think a few more people will arrive, but that's normal. I'm really happy to be introducing the 2022 version of the Al Nier lecture. The A.O. Nier lecture is an endowed lecture that is shared between the Earth and Environmental Sciences and the School of Physics and Astronomy here at the University of Minnesota. Many of you know it's in memory of Al Nier. It was endowed by Ardis Nier, his widow, for the purposes of having a regular lecture that highlighted some aspect of research that is in some way or another a legacy of Al Nier's work. And since Al Nier's legacy was so profound, that's actually quite a diverse range of possibilities. Al Nier, as many of you know, was the inventor of the modern mass spectrometer. He made contributions to geochronology and isotope geochemistry on Earth, and did many other things, including building mass spectrometers that flew on early space missions, the Viking missions. The first measurements of the Martian atmosphere came from mass spectrometers built by Al Nier. And in that spirit, we have, I'm very happy to say, Lindy Elkins-Tanton here to give what I think is the 12th Nier lecture. Lindy is involved in space exploration, as you will see, and therefore fits very well into, as I said, the legacy of Al Nier. A little bit about Lindy. She began her academic career at MIT, and then as an undergraduate, and then went into the business world for a number of years before returning to graduate school at MIT, where she studied both geodynamics and also experimental petrology, which is a field that I have some interest in. She then, following a very successful postdoc at Brown University, returned to MIT for a third time, where she was a faculty member for some time, until she was recruited away to be the director of the Department of Terrestrial Magnetism of the Carnegie Institution. Following that, she was again recruited away to be the director of the School of Earth and Space Exploration at Arizona State University. She remains at Arizona State University, but she has passed on the directorship and taken on other responsibilities, one of which is that she is the principal investigator of the NASA Psyche mission, which is going to launch later this year in August, and which is the topic of her lecture. She's also the vice president of Arizona State's, she's vice president of Arizona State and the co-chair of their interplanetary initiative. And in addition, she finds the time somehow to be a person in public science, writing popular work for publications such as Slate and Medium about science and science culture and the future of how science will work in a collaborative, interdisciplinary world. I just found out yesterday, because she posted it on her Facebook page, that she's also the author of a memoir that's coming out this spring that's entitled Portrait of a Scientist as a Young Woman, which I'm looking forward to having a chance to read. And today she's going to tell us again about the Psyche mission. Oh, I should say the Psyche is an asteroid. Lindy has an asteroid named after her. It's one of many honors that she has, including medals from the National Academy of Sciences. And in fact, last year she was elected to the National Academy of Sciences. But going back to asteroids, today we're going to hear about a rather unique asteroid that is the subject of this mission. And take it away, Lindy.
Thank you so much, Mark. And thanks an awful lot for inviting me to give the Nier lecture. I've had fantastic visits to Minnesota in the past and know many of you as friends. And so this is especially sweet, so thanks. What you're looking at right here, of course, is an artist's rendition of what the Psyche asteroid might look like. We believe that it's made largely of metal, and I'll talk more about why we might think that. And we're recently given what I used to call the talks about the ever-evolving talks about the mission that I give, Journey to a Metal World or Journey to a Metallic World. But recently we had an article in IEEE Advances or IEEE, and they called it a Electric Journey to a Metallic World because we're using electric propulsion. And I just thought that was really cute, so I thought I would use it. So important when I talk about going to this metal-rich asteroid, that I point out that, in fact, we do not know what Psyche looks like. And this is one of the really key and exciting things about this mission. We named it Psyche after the asteroid that we're going to, because Psyche is not a particularly well-known asteroid, although it was the 16th discovered. And like many asteroids, it is just still a point of light for us. And even through Hubble, it's just a few pixels. And so that beautiful artist's interpretation is almost certain to be completely wrong, as we always are when we go out into space to look at something that has not been looked at before. So this is the best shape model that we have for Psyche. It's created by a combination of light curves, reflected light as the asteroid rotates, and also radar reflection images. And there are 3 or 4 of these relatively high fidelity shape models of Psyche, and they don't agree with each other. So yet another thing that we don't really know is we don't exactly know the volume of Psyche. And if you're thinking ahead, then you're thinking about how would we know that this is made of metal? One of the key indicators might be the asteroid's density. And it's hard to know its density with great fidelity unless we also know its volume. And so there are a lot of questions about Psyche. This is the size of Psyche approximately, taking into consideration that it is sort of a potato shape. Having spent a lot of my life in Massachusetts, I like to compare it to Massachusetts. If you cut off the Cape, that's about how big it is. About 3/4 of the distance between Boston and New York. So it's quite a large asteroid. And so what do we think that it is? Well, let's go back to a little planet formation theory. If you look at the left, we start with the gas and the dust and the pebbles of the disk that became our planets around our young sun. And they quickly clumped up into these bodies called planetesimals. And for some of you, you know this perfectly. And for others of you, it might be a little far afield from what you normally do. So I'll just walk through this process. Planetesimal obviously just means little planet. And these were the bodies that were the size of cities or continents, you know, tens to hundreds of kilometers in radius. And they were the building blocks for the rocky planets. And in fact, we think that it's the remnants of the planetesimals that are stranded in the asteroid belt today. So the planetesimals collided together, and in some cases it was a destructive collision, and other times a constructive one, and it started building a larger body, later called a planetary embryo, and eventually they formed up into planets. Now, in the planetesimals, you see there, the one on the top is just different colors of brown, by which I'm meaning to indicate kind of an onion skin structure is what the asteroid people call it. It was heated by radiogenic elements and fluids probably fluxed through it, but it didn't melt. And the one underneath it melted. That's what I'm trying to show with the red. We think that planetesimals melted because of a very short-lived, very hot radioactive element, aluminum-26, that would have melted that original dust and gas material that made up the planetesimal and allow the metal component to sink into the middle and make a metal core, and the rocky component to stay on the outside. And so if we think about a body like Psyche, that, and I'll show you in a moment, has quite high density, and we think it has a lot of metal, the simplest thing to assume is that it is a part of a planetesimal core, because that's the best way we know how to clump metal together. But it really might not be. There's a whole range of things that it could be, created by the many kinds of impacts and processes in the earliest part of the solar system. And all of this happened very, very fast. The latest estimates are that Mars was probably complete in just 5 million years after the beginning of the solar system. And is 5 million years very fast? Well, it is when you consider that the solar system is 4,568 million years old. And so just 5 million years is super fast. About 100 million years until that last big impact that created the moon from the Earth. And that was maybe the last really big event in the rocky planet forming region. And so if the solar system's age, instead of 4,568 million years, if it was a 24-hour day, Mars was made in just 94 seconds. And Psyche, we think, would have been created in the first, say, 10 to 20 seconds of that 24-hour day. So it's something left over from the very beginning of the solar system. Now, here's some data. Let me just orient you to this graph. On the vertical axis is the bulk density of Psyche, the estimates people have made for how dense Psyche might be as an asteroid, because this is our very first way to think about what it might be made of. And on the horizontal axis is the year of publication of the estimate. And so before we look at the green data, look for a moment at the red lines. So that top red line is labeled camosite over on the left, and that's the name of a mineral in iron meteorites. So it's an iron nickel metal that that we know was probably the material that made up the cores of planetesimals. So that's like a pure iron nickel heavy thing. Then there's troilite, around 5,000 kilograms per meter cubed, and that's iron sulfide, it's FeS. And so we think that that was certainly a byproduct of core formation in planetesimals, also relevant to the possible density of Psyche. Then the bottom line, enstatite, is a common silicate. People have thought that they saw the signal of enstatite on the surface of Psyche. So then let's look at these green dots. If you look back before 2004, you see one person even thought, one publication thought Psyche might be 11,000 kilograms per meter cubed, which would be really hard to explain, frankly, because there's not a lot that's denser than camosite, and yet this would have said that Psyche was much denser. And then you can see how the data kind of necks down, and a key date here is 2017. 2017 was the year that Psyche Mission was selected for flight. And suddenly there was a lot more impetus for people to do a lot of studying of the asteroid, because they can quickly publish things before we get there, make predictions, and be proven right or wrong. Like, it's very satisfying in science, isn't it, when you can be making predictions about something that eventually your predictions will be tested. And so since selection, people have worked a lot harder on the density problem, and the density is kind of narrowed down into this range. The yellow one there is our team's best estimate. So it's really plus or minus about 4,000 kilograms per cubic meter, which means that it is, we think, between 30 and 60% metal, probably. That's what we published in 2020. And then on the far right, you see the density of other asteroids. Most of them are in that gray patch, much less dense than Psyche. Cleopatra, which is the densest one there, there are other estimates for Cleopatra that put it as a denser number. So Psyche might be the first or second densest asteroid out there that we know of. And so therefore, by far the most likely to have a high metal content. So that's what we know about Psyche so far in the density world. So Psyche's bulk density appears to be, say, around 4,000 kilograms per cubic meter. So we'd predict 25 to 60 volume% of metal, unless metal at space temperatures can support a lot more porosity, fracture space, void space, which is really possible, in which case it could have a much higher metal fraction if a lot of it is fractures or pore space. So we'll find out, we don't know. From thermal and radar and spectral data, the surface appears to be fine-grained metal. These are results from multiple investigators, none of them me. And then the spectra, interesting, the reflected light off of Psyche indicates a very low iron oxide content in the rock portion. This may not seem very exciting to you unless you're an igneous petrologist. It turns out it's pretty darn hard to make silicate minerals with very, very low iron oxide in them, right up against a big lump of metal like a core. And so it limits the kinds of materials that Psyche could be if all of this is true. And it helps us form up our different ideas about what we might see when we get there. So this is kind of the best data we have here on Earth. And I would just say, probably everything I tell you about Psyche today will be proven to be wrong once we get there. And so that's one of the great things about all the hypotheses about it and the news that comes out about new papers about Psyche is that, of course, we have no control over what Psyche is. And when we get there, we're going to find out. So that's exciting. And these are the best things that we know so far. So of course, we look at meteorites, which are really the library of materials we have on Earth that indicate what's in the asteroid belt, because most meteorites that we have on Earth today fell from the asteroid belt in the relatively recent past. And so one set of meteorites that matches the spectra of Psyche are the iron meteorites, and also the meteorites rich in troilite, that sulfide mineral. This all comes from very in-depth work done by Stephen Dibb in a paper that's forthcoming. So the iron meteorites and the sulfide-bearing meteorites, those are very consistent with Psyche being at least partially a core of a planetesimal. But guess what fits the spectra absolutely best? The meteorites that absolutely best match Psyche spectra are this obscure group of meteorites called the CB chondrites. And so unless you're kind of read into the bizarre literature of the meteorite world, this is not very exciting to you. So let me explain why this is so strange. These are two examples of CB chondrites. They're very metal rich. The gray shiny parts in each of these meteorites is iron nickel metal. And you can see that there's a lot of it. And do you see the one on the left, how the metal parts are circular, or they look like maybe the cross sections of bubbles? It really looks like that metal was molten and splashed into droplets and then froze. And it turns out that the silicate, which is the darker material in between the metal in both of these cases, has very little iron oxide. And so they match Psyche's surface spectra and density incredibly closely, but our best guess about how the CB chondrites were formed is that they're kind of a foamy residue from giant impacts between bodies early in the solar system, kind of like the splash after the impact. And the question is, could something as big as the state of Massachusetts be basically a foamy splash? That seems really unlikely. We would like to choose as our leading hypothesis the most likely option. Right here, we are way down in the corner of very, very unlikely. And so it's really interesting. I don't know what it's going to end up, how closely it's going to end up matching the final product. But all of this is by way of saying, Psyche is a strange object. It's really worthy of exploration. And the truth is, we really do not know what it's made of. We have 5 science objectives for this mission. And objective A is determine whether Psyche is a core or if it's some perhaps even unmelted material, something that a meteorite expert would call a chondrite, with a lot of metal, an anomalous amount of metal. That's also possible. So we'll find out. So let me talk a little bit about how a NASA mission happens. I found this quite fascinating, and I wonder if some of you who have not been involved with missions might also. It started back in 2011. When I wrote this paper with Ben Weiss and Maria Zuber, it's got a super compelling title, Chondrites as Samples of Differentiated Planetesimals. So it's a lot of jargon, and really what we were suggesting is that some of these planetesimals might have melted and differentiated into a metal core and a rocky exterior, but then also been coated with material that never melted, like have a lid of primitive material. It turns out that was super controversial. And in the tiny world of people who think about planetesimals, it caused a stir, and got an email from a couple of people at Jet Propulsion Laboratory saying, Lindy, how'd you like to work on a mission proposal to test your hypothesis? So then we went out seeking ideas about where we might go in the solar system to investigate this. So we had our first discussion in 2011. We chose Psyche as our target late in 2011, and we started working on putting together a team, convincing Jet Propulsion Laboratory to be our mission manager and put this project into their portfolio that they were going to propose to NASA. And we had to start writing the proposal, because if you start writing the proposal after the A.O., the announcement of opportunity, is released, it's too late. You won't have enough time to get it done. So the announcement of opportunity was released in 2014, and we submitted our proposal, our step 1 proposal, in early 2015. This was also, in the interest of telling the full story, a very exciting little period of time for me, because right in the middle of 2014, I moved to Arizona State University to take over the directorship. And 6 weeks later, I was diagnosed with ovarian cancer. And so I was going through desperately awful chemotherapy as we were writing this proposal. And it was just like every day I was very determined to get up and think about the space mission, because it was way more fun to think about than the healthcare aspects. And I'm totally fine now, which is awesome. And we submitted our step 1 proposal, 250 pages. We had about 40 people working on it, all volunteer. There's no money at that point. And later in 2015, we competed against 28 missions went in with proposals, and they chose 5 to move to what's called step 2, and they selected us. And it really startled me, because we were not expecting to be selected. Usually you have to go through this process more than once, if you can imagine it. And then often, of course, you're never selected. And then even if you do get selected, they look for PIs principal investigators who've been through this before. We also brought in a new industry partner in Maxar. Maxar had never done a deep space mission with NASA before, and that's usually subject to lots of scrutiny. So we were thrilled to be selected. We did not expect to win. Then we went into the giant step 2 proposal process. Here's a proposal process where NASA gives us $3 million for a year to write the concept study report. We ended up with 140 people on the team, and we wrote, I don't remember any longer how big this was. In all, it was like 1,000 pages of writing. So it might've been something like that. And then there's a huge site visit where the review panel comes and grills you, and it's this whole thing. And then much to my shock and surprise and thrill, early in 2017, I received a call from Thomas Zurbuchen, the associate administrator, saying we'd been selected for flight. Unbelievable. So then we spent the next couple of years in phase B, which is formulation, and going through reviews. Preliminary design review is on there. And then phase C, which is implementation, where we're building the spacecraft. The critical design review there. In 2020, we were the very first NASA mission to ever have a virtual critical design review. And we have experience building a very, very complicated piece of hardware during COVID. And I'll show you a lot of hardware pictures later because it's quite amazing. I think we're going to hit our launch. So we're here, and we're meant to launch in August 1st is when our launch period opens. And so there's a huge amount of stress and a lot going on the team. I've already had multiple Psyche meetings today. So if all things go well, keep your fingers and toes crossed, we'll launch August 1st. We'll then do a Mars flyby, and we'll cruise through space for 3.4 years. And in early 2026, we will arrive at Psyche and begin orbiting. This is an orbiter only. We are not landing. We are not bringing back samples. So we'll have 21 months of orbiting and science operations. That's the plan. So here's the cover of our step 1 proposal. This is another fun thing about these very big projects as you get to hire professional artists. So here's a moment of impact between 2 planetesimals. And our step 2 proposal cover is maybe 30 seconds later as one of the impactor is screaming down to the bottom left. And you can see some of the hot red metallic core being revealed on the top right. So we're trying to tell the story. Here's the image of what our spacecraft is going to look like with big 5-panel solar arrays on both sides. We're the lead at Arizona State, partnered with Jet Propulsion Laboratory, which is the mission manager. Maxar built the power system and what's called the chassis, that middle square box of the spacecraft that holds all the payload and so forth. We're getting instruments from Johns Hopkins, Malin Space Science Systems, and the Danish Technical University. Those are the top partners, but there are dozens of institutions being a part of this. The overall budget is over $900 million. And at peak, we've had 800 people on the team. We're at about 500 people at the team right now. So it's a big project. Here's schematics of the spacecraft with a person for scale. So it's pretty large. And so let me walk you quickly through what our science instruments are. You start on the top right with the gamma ray spectrometer, and below it, the neutron spectrometer. This is a very space-specific piece of equipment that actually uses gamma rays and neutrons that are emitted by the atoms on the surface of the asteroid. They're created there by cosmic rays and then emitted and captured by our instrument, which can tell exactly what kinds of atoms made those gamma rays and neutrons so that we can actually get the exact atomic composition of the surface that way. So that's how we're in orbit, but we're going to find out what it's made of. Then you can see our high gain antenna underneath that. And down on the bottom left, something called DSOC, the Deep Space Optical Comms. This is a tech demo. It has nothing to do with our science. It will not be on while we're at Psyche, but it will be on as we go past Mars. And it's a demonstration of a way to communicate with the Earth using lasers instead of radio. You can encode a lot more information in lasers, and people joke that it's like how we'll stream movies to Mars once there are people there. So we're hopeful that it will work. It'll be a really great tech demo. And then over on the right, we have magnetometers out on a boom to measure if Psyche has a magnetic field. If once it was a core, it may have retained a magnetic field, even though it would have no dynamo today, of course. We hope to measure magnetic field, and then there are cameras poking out the back. And then down on the bottom, you see SPT ion thruster. So this is what's called a Hall effect ion thruster. It uses the noble gas xenon as a propellant, and it ionizes the xenon atoms and shoots them out through a potential field And the little inertial pushes of these tiny atoms being pushed out of the thrusters is actually what moves the spacecraft. So it's very, very high efficiency and very low specific impulse. So we go slow, but super efficiently. And it's all powered with solar power. Here's what the solar panels will look like when they're stretched out. And it'll be about the size of a singles tennis court once they're unfolded. They fold up completely flat against the spacecraft's sides for launch. So you see unfolded, it's almost 25 meters, over 80 feet end to end. We're going to launch on a SpaceX Falcon Heavy, and they are going to try to land the side boosters, which I'm fairly unreasonably excited about seeing. And if that's all successful, as we hope it will be, those side boosters will then be used again to launch the Europa Clipper mission. So that's a nice cost savings. We'll launch in August of 2022, all things being equal and all of you keeping your fingers crossed the whole time. And you see during the red, there is a 90-day checkout period where we'll be working intensely to make sure everything works. The DSOC, the laser comm test, will happen during those blue dots as we go on Mars flyby for a gravity assist in May of next year. And then we'll thrust our way out to Psyche and arrive there probably January of 2026. Using ion propulsion like this, it's a little bit harder to predict exactly when we'll arrive to the day, but that'll be about it. And then we will orbit for the 21 months while Psyche continues to orbit around the sun. You see, we'll get about a quarter of a Psyche year in during our 21 months. And when we get there and we're orbiting, because we don't really know the density and we don't really know the shape and we don't really know, therefore, the gravity field, we'll start very far away in orbit A. And then as we define the gravity field better and better, we'll be able to step down closer to the asteroids, so orbit B and then orbit C. And then we'll do a plane change maneuver and go at 90 degrees to where we had been for orbit D, where we'll be closest to the surface, getting the best compositional data. So that is the plan and part of what we're hoping to find. I want to talk a little bit about teams. Mark suggested I might say a tiny bit about this. As I've mentioned already, we're at about 500 people. We've been as high as 800 people, and only a subset of those are full-time. We have lots of fractions of people working all over the place. And this is something that I'm really pretty obsessed with, how teams work. Mostly because of experiences in academia, which I call the hero model. I would say that most of academia and organizations in general are built this way. One person, the hero, owns their topic or their subfield, and they control effectively a mountain of whatever size of people and resources. And this is classically started really strongly in the 18th century, but even before that in Germany is kind of the archetype of this, where that person is the master of their field. They own a building and a lab, and they own their professorship lines underneath them, and the lab and the spaces and the students, and all under their leadership. And so there are many benefits to this model. It's served really good purposes through the centuries and gotten us really far for a millennium, but there are really two big problems with it. One is that knowledge becomes incremental, like little bits of real estate are added around the bottom of the mountain within that person's field. And you tend to bump up against the next mountain at your organization, and that's their field, and you don't really step over into that field. So keeps people in their disciplines. And the second one is culture. The hero culture is not necessarily inclusive. It's not necessarily safe for everyone. It's not necessarily a situation where the person who's leading really knows how to take care of their team or cares to take care of their team. And so if there is bullying and harassment, it can go unchecked in the hero model. And we see this in academia. There are places where this works beautifully, and people are looked after and nurtured and encouraged, and it's inclusive and diverse. But in general, I think that's been a failure of this model. And so we've been investigating a kind of a team model, where the goal question that you're trying to solve is exterior to the team rather than held only by one leader, where everyone, you have every discipline that's needed to answer that question, and everyone's working in the same direction, and you can kind of make the team culture a little different than it is sometimes under the hero model. And so I wrote a essay about this that Mark referred to obliquely last summer in Issues in Science and Technology, where I talked about ways that we've been experimenting with putting together teams in a different way, trying to make them much more inclusive, better culture, faster moving toward the outcomes that we want. And I don't mean at all to say that we should throw out all the things that we're doing now, but I think that it would be good to include some other models like this one alongside what we're doing, so that there are options in ways to move toward the results that we want and to include the kind of people that we want on their teams. And so the process that we've invented and been working on, we call the big questions teaming process. It's, first of all, it's a ton of fun if you want to try it. And second of all, it has been pretty effective. I'll just say a few words about it. We start by putting everybody into a room and brainstorming the biggest questions we need to answer in a particular field. And when I say everyone, the first time we did this was in 2017, and we had about 50 people. There were some deans and a bunch of faculty. There were graduate students and undergraduates. There were staff. There were people from the community who were not scientists, but just interested. There were people from companies nearby. And I just invited everybody. And we brainstormed these questions about what do we need to understand to have a positive human space future? That was kind of our prompt. So we wrote down all the questions everyone could think of, and pretty soon everybody's comfortable and we're just shouting out questions, we're writing them on the board. Then we voted on them. And the top 10 invited everybody to volunteer into teams around those 10 questions. And then we went into the other room and each team got a table and they had an hour or something like this to first of all make a list of what disciplines did they need that they didn't already have to make progress toward this question. And these are meant to be really big questions, questions you couldn't answer in a short amount of time or maybe even in your career. Big questions. So then decide on 1-year milestones that you could make progress on toward this big question just in 1 year. Then we choose a leader. So you don't start with the question inside the person and the person's favorite topic that they're going to do the same way they've always done everything. You choose a leader at the end. And then we put them under project management and give them a little bit of seed money. And the seed money has been between $5,000 and I think the most we ever gave was $50,000, but mostly much less than that, like $15,000, not even enough to pay for a graduate student. So far we've had 25 pilot projects over the years. Each year we renew some, don't renew some, add some more to the stable, do the big questions again. And one measure of success is a high return on investment. So we encourage them as they continue on in their project to go out and find external funding to continue what they're doing, because we just gave them a little bit of money and they need to keep going. So far, we've got a return on investment of about 7.5 times, and they've brought in so far $6.5 million in external funding. Very few of the teams have disbanded. So this is one other model, an alternative to the hero model of a single person, looking for ways to be more inclusive, hear every voice, value every discipline, maybe move faster towards some solutions. And so we talk a lot about why positive team culture matters. First of all, better decisions, because more ideas are heard and cool heads think better. I think all of us have experienced in academia situations where people of seniority speak louder and with more conviction, and they can silence other people. But if you avoid that and you let everybody speak when they have an idea, you'll actually come to better decision making. Project risk is reduced. This is really critical on flight projects like Psyche Mission, because if I thought that I could always answer every question, even though I am demonstrably not the person who is actually soldering the connection that is causing the problem, then we're not going to get to the bottom of it. And if people who are relatively more junior feel like they can't speak up, we'll never know ahead of time that something is going wrong. And so we have this motto, which is the best news is bad news brought early. Bring it early enough that we can fix it. And the only way to get that is to invite everyone to speak. Also, attraction and retention of talent, because rudeness and bullying and harassment reduce diversity. It doesn't matter what your hiring metric is. if after people arrive, they don't feel like they have a chance to succeed. And so creating a positive culture, I think, is really, really important. And of course, as you can imagine, we have varying levels of success depending on the day or the part of the team. But in general, even the small steps we've made in this direction have made such a difference that NASA told us that they saw at our review panel site visit that we had a better culture and that more people were speaking up. And that was one of the reasons they selected us. And so now I can say that asking for a better culture, more civil discourse, better manners is not a luxury, and it's not a sign that we're not tough enough. It's actually practical. And this won us almost $1 billion contract, in part because we have a positive team culture. So there's lots of good ways to argue for this now. So where are we now with this mission? So here's just since selection. You could see on that earlier calendar slide that was like this one. I've been working on this now for 11 years. And we're now about halfway through the funded part of the project since we were selected. We are 157 days to launch today. Now, if we don't launch on August 1st, barring some catastrophe, we'll be able to launch later in August or even into September, but we really hope to launch on August 1st. And so all of the acronym soup there with the red diamonds, those are all different reviews that we have to go through. We're really looking right down at the point that we're going to be hopefully having this spacecraft fly through space on its way to Psyche. So one of the first things that we did at Jet Propulsion Laboratory was with hardware was set up the test beds. So you have to have effectively a duplicate of all of your hardware sitting on shelves like this so that you can run tests with it. First of all, as you're building, and then also once the spacecraft is underway, you need to have a test bed back on Earth. So if something's going wrong, you can do lots and lots of tests here to see if you can figure out what it is. So that's me with Melody Safavizadeh, who's the woman who's the head of our test bed operation. So how did we get this together? So for the last couple of years, everyone's been building subsystems in different parts of the country and even also in Denmark. And the chassis of the spacecraft and the solar panels and the power system was up at Maxar in the Bay Area, but it had to come down to Pasadena where Jet Propulsion Laboratory is. So it gets shipped down in this giant shipping container. These shipping containers are quite astonishing. They're of course like hermetically sealed, completely instrumented up and down so that you know everything that happened to the spacecraft and every temperature and pressure fluctuation for every minute of the whole time that it's underway. And it's got fully redundant environmental control systems and the whole bit. It has to be kept super clean. You can see the people in their gowns. And the thing that cracks me up is that Maxar has stenciled on the side, spaceflight hardware do not drop, like someone would forget and drop it. I just don't know why they do that, but it makes me laugh every time I see that stencil. So it was shipped down and arrived at Jet Propulsion Laboratory in March of 2021. And so there it is on a hoist, that polygon from the ceiling, the white thing is the top of the hoist. It's been taken out of the shipping container and it's being guided. And you see people holding ropes so that it doesn't swing onto that disc you see on the right. And so that's actually the ring that hooks onto the ring on the bottom of the spacecraft and holds it on what's called a dolly that holds the spacecraft up and turns it around and tilts it back and forth so that the people who are building it can reach all the parts of it. And you see on the left there, those are the booms that are going to hold the gamma ray neutron spectrometers and the magnetometers that you saw in the schematic. So it arrives in March, ready for the part of the project that's called assembly, test, and launch operations, which is what we're in now. So this is me and Henry Stone, who's our project manager and the guy who manages the whole thing at Jet Propulsion Laboratory shortly after delivery, standing in the high bay with the spacecraft, which was like a crazy, thrilling moment in my life to see it there. And you can see, I am not an engineer, but I got to do the whole gowning up process, which is actually also a sort of ridiculous thrill. And if you've ever done this, the high bays at JPL and other places are very clean rooms, but they're huge. And you go through many steps to get into them. And the last step is an air shower, where you step into a little room the size of a phone booth that has a door in, a door out, and the other walls and the floor and the ceiling are covered with air nozzles. And it sprays you with air and sucks the air out while you hold your arms up and dance in a circle to try to get all the particles off you, even after you're all gowned up and cleaned up and suited, to be as clean as possible. And after a minute of air showering, the other door opens, and then you get to walk out and see your spacecraft for the first time. So that was a great moment. So here's another view. This is High Bay 2 at Jet Propulsion Laboratory, seen from the viewing gallery. And you can see the people there for scale, and there's the spacecraft on its dolly, and they're building it. There it is. So the magnetometers were delivered from Danish Technical University in May of 2021. These two unbelievably high performance, incredibly fabulous little instruments. And we installed them onto the booms. There they are on the boom. And then here's the Deep Space Optical Comm tech demo installed last July with part of the team. It's that whole silver wrapped polygon there. It's actually a huge instrument, and accommodating it on the spacecraft has been really hard. And so I really, really want it to work, because it was hard for us to do. And we really want this tech demo to work, and the team's been unbelievable. 1 year to launch in August of 2021. This is the hero shot that they took that was released on a press release. And you can see in the side of the spacecraft, the panel's not on yet. You can see those red tubes. Those are nitrogen gas tanks for some cold gas thrusters that we'll use for a little station keeping once we're in orbit, not for the propulsion to get there though. Here's the gamma ray and the neutron spectrometer delivered from Applied Physics Lab in August of 2021. They, like a lot of these groups, send this unbelievably precious, completely irreplaceable flight hardware via FedEx across the country, and it gets tracked, and you can see it going across, on a map, and it goes in climate-controlled cases with instruments and the whole thing, and then they get an email, your package has been delivered, just like it was, some kind of FedEx letter or something. It's very nerve-wracking, because there is no backup instrument. And if this instrument was wrecked en route, it literally would cancel the whole mission. So there are a lot of nail-biting moments there. So there it is, installed on the boom with the gamma ray at the end and the neutron spectrometer wrapped in foil already down the boom in August. Then we installed the Hall thrusters. These are the SPT-140 ion thrusters. You see them on the left with those red caps and the white arm. It has an arm that articulates out from the spacecraft. You can see the two arms on the right with the guys working on it. Everything that's red, like those caps, is removed before flight. And so those tops will be taken off. One of the things we need to do is make sure that the arm worked, but the arm is designed to work in zero gravity. And so to work on Earth, it needs this big angle iron looking thing that's on the far left to unload the weight of gravity, to hold it up against gravity, but not interfere with the arm doing its motion. And you can see on the right, the two techs staring up at it anxiously while it practices unfolding and refolding. And so that was successful. And then this was the NASA image of the day in October. The Hall thruster on the right, and on the left with the blue, that's a test fire. And the blue is ionized xenon, and it's in a big vacuum tank with a window that you can look through to make sure that it's working right. And so that is what the thrusters will look like in space, very Star Wars. Then we prepared for all the tests. And so the first set of tests on the fully assembled spacecraft here is system environmental testing, which is electromagnetic interference and compatibility. You need to turn on all the systems, make it live, turn it on, as they say, and then make sure that everything works together electrically and magnetically. And it has to be shielded from outside electromagnetic effects. And so it goes into that tent, which is actually a huge Faraday cage made of conductive materials. So the spacecraft passed its Emi Emc testing through the holidays. Because it is so hard to build things through COVID, and we had to keep everyone well, and we had to deal with parts delays and people getting sick and having to stop everything and sterilize everything. And you can imagine how hard this has been. The slack in our schedule went away. And so all of us worked every day through the holidays except Christmas Day and New Year's Day, but every other day we worked. Then the next step is to go into the thermal vacuum chamber, where the spacecraft, it's just the bottom of the spacecraft, that you can see on the right. See the person there for scale, one up on the viewing gallery and one down at the bottom. Putting the spacecraft into this giant chamber, and a big door slides back over that big gap. And the whole chamber is a vacuum chamber. It's this thing, I so love this. It's so geeky and fabulous. It's 25 feet across on the inside, and it's, I don't know what it is, like 70 feet tall or something. So you can put big spacecraft in there, and then you can evacuate the chamber down to space vacuum, and then you can freeze it down to space temperatures, but you also have to be able to shine sunlight on it, because sunlight is very hot in space. And there's usually a big thermal gradient across the spacecraft from very hot on the sun side to very cold on the non-sun side. And they actually have the ability to do the equivalent of 40 solar constants, 40 times the sun at the Earth, for spacecraft that are going closer to the sun. Now, we're not doing that. So luckily we didn't have to use that. So we ran 18 days of tests in the thermal vacuum chamber. We found 2 problems that we're in the process of fixing. So that's actually quite good. And then the most recent thing that we've just been doing this week is practicing with the solar panels. And so that is 1 solar panel, and each side of the spacecraft has 5 of those. And so that's what one side looks like, folded up, all 5 on top of each other. And unfortunately, I don't have the movie to show you, but we practiced unfolding them there on that rig in the high bay. And it was just a beautiful sight to behold, how big those solar panels are and that they completely unfolded. It's 20 kilowatts of solar power here near Earth, and about 1/10 of that by Psyche. So that's a kind of summary of the Psyche mission and all the things that entails. That's me on the left peering up into the spacecraft with Brian Bone on the right, who's our ATLO Assembly Test and Launch Operations Manager. We were looking at the communications panel. And so if you're interested, feel free to follow us on, we have Mission to Psyche, and also myself on Twitter, and Mission to Psyche is also on Facebook and Instagram. And we have a website. We have ways that students can be involved and the general public. And along those lines also, because the whole team really believes that space exploration is for everyone, one thing we're going to be doing is we've actually created, we're in the last bits of creating a pipeline that will allow us to take the images that are going to come from the spacecraft and stream them live on the internet within a half hour of our receiving them. So we're not going to edit them and censor them or anything. We're going to let everyone in the world look at the pictures at the same time as we are, and we can all scratch our head at the same moment and wonder what it is that we're seeing. So thank you so much for the opportunity to give this lecture, and I'm excited to answer questions if there are any.
Thank you, Lindy. That was great. I see lots of hands quietly clapping. Something that is a tradition in the Earth and Environmental Sciences Department when we have seminars is that before the faculty jump in, we reserve a time for the students to ask questions. So if students have questions, you can either raise your hands or type them into chat. And while we're waiting for that, I'll just ask a question that will sort of fill in the time until that. When you said things about CB chondrites, I thought, oh, that's weird. Yeah, she's right, that's weird. But then I also thought, if you're going to excavate something the size of Massachusetts, that's a lot of energy. Do you have simulations to indicate, that maybe melting is in fact probable to excavate the interior of a body that size? Or is anybody investigating that?
I'm sorry, I didn't quite understand. Melting is probable, melting during excavation?
Just to shatter a planetesimal of that size.
Yeah, right. So this is one of the real troublesome aspects of this, is that if we do think that it's really largely made of metal and probably a part of core, how do you make that core visible? How do you get rid of all that rock? And even if it was a small planetesimal, like the smallest possible one might be about the size of Vesta, and you'd have to remove most of the rock. And so Eric Asbog has been running 1 million simulations, and many of his team have been working on this. And it would take like 4 to 11 impacts that we're stripping material off and no impacts adding material to make the core visible. This is a highly unlikely event. Maybe once or twice in a solar system formation process does that happen in simulations. Or you could have a smaller object hitting a larger object that would virtually, they call them like a hit and run collision, that would virtually strip the outside of the smaller object off as it kind of passed through or alongside the other one. So there are a bunch of different scenarios with different size bodies, but none of them are super likely. You are right about that.
I see 2 hands raised. Jennifer, can you ask your question?
Hi, this isn't actually Jennifer. This is Untitled using Jennifer. First off, I just wanted to say that was a great talk. I really enjoyed how you showed what goes into like a successful NASA proposal without outside of the scientific merit alone. So that was incredible.
Oh, cool, thanks.
My question was related to, so the 2 main hypotheses are that it's between a CD chondrite or like a representative iron meteorites. Could you talk a little bit about the redox implications of that, or like at least where that could tell us about where it was formed in the protoplanetary disk?
Oh yeah, so that's a great question. So the question is really, how much oxygen activity would there be? Because if there was a lot of oxygen around, or oxygen activity, then all of that iron metal would become iron oxide, and there would be iron oxide in the rock component. And so you think it would have to be pretty darn reducing. So either a core mantle boundary or a high temperature of an impact also makes it very reducing. So our guess is that it would be highly reducing, but we're going to be looking for a bunch of clues. That's one of our science objectives, actually. Exactly, you hit it straight on, to figure out how reducing it might have been. And so Tim McCoy from Smithsonian is working really hard on that with us. One of the indicators will be how much nickel is in the iron metal. So hopefully we'll see enough iron metal that we can measure its nickel content, and that will tell us also something about the oxygen activity or how reducing it would be. I'm not confident myself that we're going to be able to say where in the disk it came from. First of all, because I think that our understanding of the state of the disk and the different compositions of it is pretty darn imperfect and non-unique. And so we'll see what we can discover. And maybe we'll be lucky and get a lot better data than I'm anticipating, and we'll be able to come to a lot more conclusions. We'll see.
Thank you.
Is another question from someone named FDB, I suppose?
That's right. Can you hear me?
Yeah.
We can hear you.
Fred, University of Michigan, Ann Arbor. I'm a graduate of the other MIT, Minnesota Institute of Technology. When it was
excellent.
And I got into physics and nuclear physics in particular when I wandered down in the basement at the physics lab, physics building at Minnesota, and walked into Nier's lab where they were doing a mass spectrometer doublet measurement of some nuclear isotopes.
How amazing.
And he was kind enough to explain it to him. I kind of knew who he was, but I realized later he spent all that time with me explaining what he was doing. And I was so fascinated, I wanted to work with him, but he didn't have a position available. He sent me down to the nuclear lab where I eventually got my Ph.D. Anyway, so in honor of him, I've built several mass spectrometers for teaching, and we published an American Journal of Physics measuring neon isotope abundance in the atmosphere as a teaching. And so I also work in nuclear physics. And what actually is your neutron spectrometer? You said spectrometer, but do you actually measure neutron spectra, or you just detect neutrons?
We just detect them. So we have low, medium, and high energy range.
Okay.
Those are just neutron tube detectors. Yeah, we get the really specific stuff from the gamma ray spectrometer, and that is the detecting element there is a giant high purity germanium crystal the size of a baseball.
So that was a refrigerator built on there. There was a refrigerator on there, I guess.
Yeah, we have a cryo cooler.
Cryo cooler. Okay, gotcha.
Yep, yeah. Yeah, okay. So for those of you who are not like right in this field, I learned about this. This was not my field. So this is, I've heard that this germanium crystal is the highest purity material humans make. It's this huge crystal, and it's sort of green, which is really fitting, and it can detect the strikes of these gamma rays. And but all the space radiation eventually causes defects in the crystal. Right. Well, first of all, it detects best at very low temperatures. So even in space, we have to have a cooler to make sure that all its heat is gone and that it's kept as cold as possible for detection. But then when it gets a lot of flaws in it, we actually have to anneal it by heating it up to its annealing temperature. So this is a very complicated instrument. It has to be able to heat itself up cool back down, and then go really cold for detection, and then later heat up again. It's
That was applied. It's hard to do that on Earth, let alone in space. So
yeah.
that was applied physics. And so your neutron detector is just an energy selection detector.
That's
So
right. That's right.
I actually work with, I
developed
developed detectors. We actually have neutron spectrometers. We're thinking about putting up in space somehow, and we can actually measure the neutron energy levels, which would be kind of fun.
Get it on test flights.
But it has to be space rated, the shake and bake and thermal cycling, and I'm not sure it'll survive that.
You have to actually fly it and raise its technology readiness level, and then someone can propose it on a mission.
Yeah. So thank you very much. Enjoyed the talk. You know about clocks and rocks, dating Earth and other artifacts.
I think we need to open up the questions to the rest of the.
Okay.
Thank you very much. Oh, so we've given a chance to graduate students. The questions are open to anybody else.
No questions. What a quiet crowd.
I'll ask one.
Awesome.
I was curious about the resolution with which you'll be able to image the surface. So I understand it's so cool that you're going to go start out far and then zoom in. So how, like, I assume you won't be able to do the kind of comparison to the chondrite that you were showing where you can see the bubbles and stuff like that.
I know.
But so what's the next best thing, I guess, like how when you have a high resolution picture, when you do get as close as you possibly can, what are the things that you're going to look for at that really high resolution, and what can you will you be able to resolve?
Yeah, so we'll get down to the point where it'll be a couple of meters per pixel. So we'll still be like 70 kilometers away. So I wish we could get down to the centimetric scale. That would be amazing. But the cameras that we're flying, the images we're flying, have filter wheels, and the filter wheels have filters on them designed to look for the absorption features of specific minerals, really. And so I think that we're planning that with that filter wheel, we'll actually be able to tell on that smaller pixel scale kind of what the metal to silicate mixture might be. Because a big question we have is, if it really is a part of a core, then we would expect to see, tens of meters, hundreds of meters, kilometers of metal areas. But of course, the surface is fine-grained. It's been broken up over time. But if it's primitive chondritic material, you'd expect the silicate or the non-metal part, whatever it is, maybe it's carbon, God knows what it is, but the metal and the non-metal to be mixed on a fine scale. And so the imager filters will be able to tell us something about that, even though we won't be able to see it directly. Yeah.
Neat. Thanks.
Thanks for the question.
There's a question in the chat that I
Oh, yeah. Okay. Is there an opportune time in Psyche's year to study it from orbit? That is 100% correct, because Psyche's spin axis is knocked over into the ecliptic. So it's spinning like a rotisserie chicken instead of like the Earth with the spin axis upright. So what that means is, you could imagine that if one hand is the sun and the other one is the spin axis, there's a time when only the North Pole faces the sun. Then there's a time when it's spinning and all of it's being illuminated. And then there's a time when only the South Pole is facing the sun. And so if we go when only one of the poles is facing the sun, we can't get pictures of the whole body because a lot of it'll be dark. And so it was very important that we go at a time that we will get optimum lighting conditions during some part of that 21 months. So that was a big part of the planning of the trajectory and when we would arrive. So that's a really important question. And the corollary to that, though, is that also the poles of Psyche get very, very cold for half the Psyche year and very, very hot for half the Psyche year. So they have a lot of thermal stresses, which I'm hoping to kind of see. Let's see.
Yeah, the next question might require some summary, but.
So let's see, are we using particle XRF for element ID, and then how could we explain to the layperson how measuring gamma rays and neutrons identifies the materials? Right, so I can kind of answer that in one go, which is this. So there are very high energy particles or radiation that zoom through all of the universe all the time, cosmic rays. Some of them come from the sun, but other ones come from the black holes at the center of galaxies. I mean, they're pretty exotic, crazy things. And so they hit the surfaces of things all the time. And because Psyche Asteroid has no atmosphere around it, they strike the surface directly. And so when a poor hapless atom is struck by a cosmic ray, it goes into an excited state. And then when it releases that energy and its electrons drop back down again, it releases the energy in the form of a gamma ray and a neutron generally. And that gamma ray has a very specific energy that is unique to that atom. And so we can actually measure the amount of energy that each gamma ray brings to that germanium crystal and know what atom released that gamma ray. So that's how we're going to know what it's made of, because we actually can measure the energy ranges of the gamma rays that strike that crystal. So hopefully that was an okay description for a layperson as well. Let's see, information about the scale of pixel resolution so that observers would know the size of the images. Oh yeah, so with every image that comes out, there'll be information about the scale, because depending on what orbit we're in, there'll be a whole different scale per pixel for sure. Oh yeah, diverse team. So this is such an interesting thing. It's I could go on about this at a length that is not appropriate for this format, but picking the science team for a mission is a really difficult political, diplomatic, strategic project. And I try to think of we don't have a science team and an engineering team. We have one Psyche team. That's one of the things we've worked on really hard. So when we have team meetings, it's an all team meeting. So every kind of engineer is invited, all the scientists. And so, you know, on the science team specifically, we have people who do models of planetesimals and asteroids. We have people who do models of the dynamics of the solar system. We have people who are experts in meteorites and materials, and people who are experts in magnetic field. Oh my gosh, that's kind of what's come to my mind just really quickly, but there's more. Oh, gravity science, how you figure out the gravity of things. But then at our team meetings, we also have people who run budgets and the finances, and people who do the schedules, and people who are the project managers, people who do the outreach and the comms and the media connections, you know, every aspect of the kinds of work that go into a project like this. I think it's really, really important for every person, first of all, to have an introduction to what the other people do. So we do, they're like primer talks, where you just explain what you work on and how it relates to the mission. We call them Tim talks, because it was Tim McCoy who first suggested we do this. And we record them so new people on the team can learn what every other discipline is really about. And then the scientists begin to understand how complicated it is from an engineering point of view. And the engineers begin to understand what science we're going to do. And the schedulers begin to understand why people are missing the schedule and like how much it costs, like all that stuff. And so that's really, really helpful and interesting. And thanks on the healthy culture. I'm really trying, you know, nothing is perfect, but at least talking about it really does make a difference. Let's see, I think that is mostly what we've got there.
Yeah.
We've been, just one other note about diversity. The science part of the team is not as diverse as I would like. And I recently discovered that I actually have much more free reign in figuring out the structure of it than I had thought. And we are going to open up a bunch of junior investigator opportunities for people, even for graduate students whose advisors are not on the science team, because that's one of the things that's usually hard is as a grad student, you can't get involved unless your advisor is. So we're finding ways to do that. On the engineering team, we are exceptionally diverse. In a lot of our engineering related meetings, like it's gender balance is about even, there's a lot of people of color, and partly people have wanted to join the team because they've heard that we're nicer to each other. And I just really appreciate that, and I hope we keep being nicer. What happens to
I like this question.
Yeah, what happened to the spacecraft after the mission concludes? So we're hoping we will get an extended mission that will allow us to take the risk of going down closer and closer to get better and better data. And in the end, we will crash on the surface of the asteroid. We're not planning right now to consider going anywhere else, because Of course, we all know that the asteroid belt is not like what we saw on Star Wars, where you're having to like dodge them. They're actually really far apart from each other, and there's no other good candidate near Psyche toward the end of our mission. So we're just going to try to learn more and more about Psyche. Oh, what can we learn when it crashes? I hope that we'll crash on the side at a time when we can watch it from Earth and see what kind of light is produced and whether we actually make a little impact or not. We're not allowed to say land, but we have this kind of, because land implies to Congress that it survives and keeps communicating. But we do have this kind of fantasy that we'll be able to communicate data right up to the last minute. Let's see, once the elemental composition of the surface of Psyche is determined, what to anticipate will be that knowledge's effect on either planetary formation theory or stellar core formation, stellar core theory. Boy, it's hard to know what the effect would be until we find out what it is. But what I'm really hoping for is that it's a kind of material we haven't looked at before, either a piece of core or some super reduced material with lots of extra metal, and that it'll give us some more constraints on how we think rocky planets are formed, because we sure do not have the whole story. You know, we're trying to do this mystery hunt looking back 4.5 billion years. And so I'm hoping that Psyche will be an important piece of information to help constrain models about how this all came to be.
All right, it's a few minutes after. If anybody urgently wants to get a question in, they should do it now. If not, well, just a thanks. That's great. We all say thanks. Thanks very much, Lindy. That was great. I'm sure if people want to follow up, Lindy's an extraordinarily busy person, but if people want to follow up, her contact information is available, and by all means, I know you can correspond with her.
I will do my best to answer anything that comes along, and I just really appreciate you all coming and listening today. Thank you.
I can clap audibly, but everybody else can either clap audibly or do it
Thanks a lot.
with their emojis. Thanks, Lindy.
I appreciate it. Thanks an awful lot. All right, take care.
Jen, are you still there to stop recording?